For the first time ever, physicists detect signs of neutrinos at Large Hadron Collider. Scientific first at CERN facility, a preview of upcoming 3-year research campaign. The International Forward Search Experiment team, led by physicists at the University of California, Irvine, has achieved the first-ever detection of neutrino candidates produced by the Large Hadron Collider at the CERN facility near Geneva, Switzerland. In a paper published on November 24, 2021, in the journal Physical Review D, the researchers describe how they observed 6 neutrino interactions during a pilot run of a compact emulsion detector installed at the LHC in 2018. This significant breakthrough is a step toward developing a deeper understanding of these elusive particles and the role they play in the universe. He said the discovery made during the pilot gave his team 2 crucial pieces of information. First, it verified that the position forward of the Atlas interaction point at the LHC is the right location for detecting collider neutrinos, Feng said. Second, our efforts demonstrated the effectiveness of using an emulsion detector to observe these kinds of neutrino interactions. The pilot instrument was made up of lead and tungsten plates alternated with layers of emulsion. During particle collisions at the LHC, some of the neutrinos produced smash into nuclei in the dense metals, creating particles that travel through the emulsion layers and create marks that are visible following processing. These etchings provide clues about the energies of the particles, their flavors, tau, muon, or electron, and whether they're neutrinos or antineutrinos. According to Feng, the emulsion operates in a fashion similar to photography in the pre-digital camera era. When 35mm film is exposed to light, photons leave tracks that are revealed as patterns when the film is developed. The phaser researchers were likewise able to see neutrino interactions after removing and developing the detector's emulsion layers. Having verified the effectiveness of the emulsion detector approach for observing the interactions of neutrinos produced at a particle collider, the phaser team is now preparing a new series of experiments with a full instrument that's much larger and significantly more sensitive, Feng said. Since 2019, he and his colleagues have been getting ready to conduct an experiment with phaser instruments to investigate dark matter at the LHC. They're hoping to detect dark photons, which would give researchers a first glimpse into how dark matter interacts with normal atoms and the other matter in the universe through non-gravitational forces. With the success of their neutrino work over the past few years, the phaser team, consisting of 76 physicists from 21 institutions in 9 countries, is combining a new emulsion detector with the phaser apparatus. While the pilot detector weighed about 64 pounds, the phase RNU instrument will be more than 2,400 pounds, and it will be much more reactive and able to differentiate among neutrino varieties. Given the power of our new detector and its prime location at CERN, we expect to be able to record more than 10,000 neutrino interactions in the next run of the LHC, beginning in 2022, said co-author David Casper, phaser project co-leader and associate professor of physics and astronomy at UCI. This is an incredibly nice tie-in to the tradition at the physics department here at UCI, Feng said, because it's continuing on with the legacy of Frederick Reines, a UCI founding faculty member who won the Nobel Prize in Physics for being the first to discover neutrinos. We produced a world-class experiment at the world's premier particle physics laboratory in record time and with very untraditional sources, Casper said.